Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about how we can use electrochemistry to measure the concentration of specific species. So there are several ways we can do this, but one of the simplest one is to simply set up an electrochemical cell, where one cell we know the exact concentrations of all the species we care about. And in the other cell, we have some sort of concentration that I don't know. So one example we could use is to try and set up a concentration cell where we have silver on both sides, but on the cathodic reaction, I know the exact concentration of silver ions. And on the anode, I'm trying to figure out the amount of silver being released from a solid. So if the only source of silver is from the electrode, which isn't going to produce any, or from the dissolution of a silver solid, then I should end up having some low levels of silver that I can measure, again, using this concentration cell. So let's go ahead and say our cathode has a reference of 0.1 molar silver. Well, so our cathode reaction is going to have that silver ions as the reactant and the silver solid as the product. And reverse, our anode will have that saturated silver as the reactant. So we can go ahead and try and set up a reaction so we can determine the concentration of that saturated silver ions. So again, if we set products and reactants, the solids won't matter that much. And I start with that 0.1 molar silver as my reactants and the unknown concentration of silver as my products. So trying to set this up, the next step is going to set up a Nernst equation. Well, here we get pretty lucky because we can measure the potential, again, just using a voltameter, as a little over 0.4 volts. And because this is a concentration cell, I know that the standard state potential is 0. Then all I need to do is find the number of electrons being transferred. In this case, 1, R, T, and F are all going to be constants, and at a temperature of 25 degrees, I can set them just equal to 0.0257 volts. That means that the only thing I have left to solve for is the concentration of silver in that saturated solution. So then what I can do is divide both sides by that 0.0257. That way I can express it as a natural log and as a number. Then to undo natural logs, just as a reminder, we can raise both sides to the exponential and then multiplying both sides by 0.1 molar, again, being my denominator, I can get the concentration of my silver ions in my anode as about 9 times 10 to the negative 9th molar. So congratulations, you can find the concentration of any number of ions using this idea of concentration cells. But this actually has a lot of use. As I said, if I just put in silver iodide without any extra iodide or silver, then it turns out that concentration of silver ions will be the same thing as the solubility of silver iodide. And you can actually use this to back out things like the KSP of silver iodide. And so when we had all those fun KSPs and equilibrium constants over the last several months, this is one of the ways that they've actually been obtained through these electrochemical measurements, which is actually fairly impressive. However, there's often some more elegant ways you can measure the concentrations of species of ions rather than just trying to set up a full electrochemical cell. One popular approach is to use what's called an ion-sensitive electrode. So what you have in these cases is an electrode where you have some sort of electrode hooked up to a solution. And the solution is inside a glass membrane, which usually has a slightly porous part of the membrane at the bottom, which only allows specific ions to get through the membrane. Not, in this case, ion-sensitive electrode. And so that ion can then approach usually a silver electrode, which can then be connected to a known reference solution. So if you're trying to find the concentration of silver ions, you would have a silver solution in that reference electrode. If you're interested in the proton concentration, you'd have free protons of a known concentration inside that reference solution. However, just to make sure that you keep both cells at known concentrations, there's usually some sort of benchmark electrode with a known potential that you can always compare against. The most common kind is what's called the silver-silver chloride electrode, where you're using a silver solid and a silver chloride solution. One of the nice parts about this solution is because it contains two solids, and it's only slightly dependent upon the solution of chloride, which can often be controlled. You can go ahead and keep this system at a known potential over a long period of time. So one of the more common types of these ion sensing electrodes that you've actually used is a pH electrode. So for a pH electrode, you have a reference solution of about 1 molar proton. So this would be a pH 0 solution inside a reference element. And then you have a glass membrane that allows protons to come through from the exterior solution. And really what you're doing is using this electrode sensor to determine the concentration of protons versus this 1 molar proton using a concentration cell, measuring the voltage, and using that to convert to the unknown proton concentration, rather like we just did. And so one of the cool features here is, as long as the temperature is well known and controlled, such as room temperature, what you can do is convert in between potential and protons. So this little notation of potential versus the natural log of protons is a little bit cumbersome. So it's often a lot more convenient to go ahead and convert that natural log into a log. And that's done by simply multiplying your coefficients by a well-known constant. And this produces a relationship of potential versus the log of protons with a coefficient of about negative 0.059 volts. But wait a minute. We now have a relationship in between potential and the negative log of proton concentrations. It turns out that potential is a very natural way to measure the pH, as using one of these electrodes, again, assuming that you've maintained a healthy reference solution, your potential is just going to be equal to 0.059 times the pH of the solution. And so that's actually fairly convenient. However, there's a lot of things that do break down in reality. Most notably, the concentration of those protons inside that reference cell can change. Some of the protons could essentially react, leave, enter, so forth. So as a result, there's two things that are very important that you do with your electrodes. The first is that you always calibrate your electrodes. So by calibrating, you go ahead and first have 2 or more known solutions that you measure the pH, and then you can use this to back calculate to make sure that the concentration of your reference solution hasn't changed. The other important feature is to always keep your electrodes, especially pH electrodes, moist and in a storage solution. This way it prevents any of your reference solutions, either the one used for the silver chloride solution or for the proton solution, from drying out. And it is worth noting, while we are most familiar with using pH electrodes, there's a wide variety of other types of ion selective electrodes used. As I stated previously, you can do a silver electrode, a silver sensing electrode, lead, which is very useful in environmental. Similarly with ammonia, which has a lot of implications with fertilizer and water contamination, fluoride, which is very popular in trying to maintain teeth, as well as sodium, potassium, and a lot of your other alkali and alkali earth metals. So there's a lot of use in these ion sensing sensitive electrodes. So next time we're going to go ahead and take our new understanding of electrochemical cells and try and look at electrolytic cells. So instead of using chemical cells to produce energy, what type of chemical reactions can I drive if I put in energy? Until then, take care.